Dynamic Learning Maps Alternate Assessment System is a new assessment designed to more validly measure what students with significant cognitive disabilities know and can do. This training focuses on algebraic thinking and supporting its development. This training, Algebraic Thinking, is one in a series that supports teachers of students with significant cognitive disabilities in their efforts to teach and assess. Sponsored by a grant from the U.S. Department of Education, Office of Special Education Programs, this training is part of professional development efforts of the Dynamic Learning Maps Alternate Assessment Consortium. The DLM essential elements require teachers to think creatively and flexibly about their approach to mathematics instruction. As emphasized in other DLM presentations, it isn't enough to use approaches that require students to learn individual or specific answers, but rather to use approaches that encourage students to use their knowledge and understandings of known information to solve unknown problems. Approaches that support the development of algebraic thinking accomplish both of these things. The essential elements address algebraic thinking in high school, middle school, and elementary school. It begins with very early mathematic concepts in elementary school. At this level, algebraic thinking involves helping students make connections and describe and justify general patterns and recognize regularities in operations, as well as properties of number. For example, an early counting connection to algebraic thinking is learning to add by counting on from the larger number or learning to count on to solve problems like 9 minus blank equals 4. This involves the understanding of equality. The left of the equal sign is the same as the quantity on the right of the equal sign. As in the equation 3 plus 4 equals 5 plus 2, or 9 minus blank equals 4. If they are not equal, then we describe them as less than, greater than, or unequal, and use the symbols for these inequalities. In middle school, this transitions as students begin to understand that a letter or variable instead of a blank or a box can represent missing numbers. We don't know the value, and we want to find out what it is. Or we don't yet know the value and want to be able to make a formula so that we can use the value when we get it. For example, finding the area of a set of different rectangles whose width is 3 units, but whose lengths will vary. We can write the expression A equals L times 3, so that the equation is ready for calculation once we know the length of each of the different rectangles. Finally, in high school, students are deepening their understanding and becoming more fluent in the use of variables by applying their knowledge of formulas to calculate volume, area, perimeter, and mass, and using variables in equations with all operations: addition, subtraction, multiplication, and division. There are 4 important instructional goals for you to keep in mind as you help students develop their algebraic thinking. We will discuss each of these approaches in more detail. For now, the first approach involves providing multiple means of representation. This requires you to provide students with many different examples and learning opportunities using different formats and materials. The second approach is to ask questions that encourage thinking. This means going well beyond yes-no questions and other closed-ended questions. A third approach involves building on students' understandings. Finally, help students to make connections, describe, and justify general patterns and regularities in operations and properties of number. The first approach, providing multiple means of representations, is one of the elements of the Universal Design for Learning. It was discussed in detail in the module on Universal Design for Learning, as well as the modules on forms of number and units and operations. Now we want to take this concept and show how it applies to algebraic thinking. As a reminder, representations can take many forms. This may involve manipulatives, words, symbols, pictures, diagrams, tables, or graphs, or a combination of two or more of these. And we use representations to organize, record, and communicate mathematical ideas. Select, apply, and translate representations to solve problems. And finally, we use them to model and interpret mathematical equations. The point being that students will learn to use representations in a variety of ways. Throughout their mathematical development, and specifically in developing algebraic thinking, students will need numerous interactive experiences combined with explicit instruction, as well as teacher and peer models in the uses of each of these representations. When students are able to use representations, then it allows teachers to observe student thinking and discover their understandings and misunderstandings as they watch how students use the manipulatives and other representations to solve mathematic problems. For example, if I give a student the 10 frame and 12 chips and ask the question, "What can you tell me about 7?" the student may put down 7 chips. Now I know the student understands the quantity of 7. If he or she put down a different amount, the teacher may have to probe further in order to understand more about what he or she is thinking. Other examples of questions that support algebraic thinking in this context includes, how does 7 compare to the number 10? Are there any other numbers that represent the number 7? Is 7 more or less than another number? Use 2 sets of colored chips. How many different ways can you make 7? Questions such as these encourage students to think about numbers flexibly and help them make connections, describe, and identify patterns, and allow teachers to see how students represent their thinking. Pause for Activity 1. Developing an understanding of the equal sign is a very important concept in algebraic thinking and links back to the goal of helping students make connections, describe, and justify general patterns and regularities in operations and properties of number. Generally, students think that the equal sign means that they should calculate the numbers before the sign, and the number after the sign is the answer. In the module on calculating accurately with addition, we discuss various structures of addition. There are similar structures for other operations, but the most common structure is the addition joining structure, where the result is unknown. This is the example on your screen. However, it is important to expose students to the other structures so that they can come to understand that the equal sign tells them that both sides of the equation represent the same quantity. We want to avoid leading them to believe that the equal sign tells them to calculate. In the problem, 7 plus 4 equals blank plus 5. The majority of students would say that the answer was 11 or 16 because they don't understand that the equal sign actually means that the two sides of the equation have an equal quantity. Equality is the relationship expressed by the idea that two mathematical expressions hold the same value. Using a wide variety of structures will help students learn to be flexible in their thinking while developing the understanding of the concept of equality, rather than learning to recognize a specific set of number sentences as equal or unequal. Students need this understanding to think about the relationships expressed by number sentences. For example, the number sentence 5 plus 7 equals 6 plus 6 expresses equality or a true statement, while the number sentence 4 plus 3 equals 5 plus 5 expresses an inequality or a false statement. We can begin with the very early concept of comparing quantities and modeling the equal sign for students as they determine if the quantity in the sets is the same or different. In this case, students are given two mats with an equal number of manipulatives so that they are the same. Students will communicate the quantity in each set or indicate same, and then the teacher will model the additional representation. Yes, these are the same. We can also write it like this: 8 equals 8. As a next step, students can determine if one set has more than, less than, or an equal number compared to another. In this case, the teacher would represent the tens frame with 6 and ask the students to determine how many. Then the teacher could present the second 10 frame and ask the students to determine how many. In each case, the teacher could write the quantities to model the equation that is 6 is less than 9, while asking the student if the first 10 frame has more than, less than, or the same quantity as the second 10 frame. Developmentally, we need to remember that students will understand equality relationships involving collections of objects before they understand the symbolic relationship using the equal sign. But we are building on their understanding over time and using these collection-based opportunities to model the symbolic notation. Another one of many ways that teachers can help students develop an understanding of equality is using scales. In this case, teachers can concretely show the relationship of equality by using the balance and having students build equations using manipulatives to prove that the two sides are equal. This can be done with a simple equation like the one on your screen. 4 plus 1 equals 5. Or for a more complex equation like 5 plus x equals 9. Finally, understanding equality as a relationship can be seen through an even more complicated equation. 3x plus 20 equals 47. Many would begin to solve this equation by subtracting 20 from both sides of the equal sign. Why does this work? Because the equal sign signifies a relationship between the two expressions. If the two quantities are equal, then 20 less of the first quantity must equal 20 less of the second quantity. So understanding that expressions on both sides of the equal sign hold the same value can aid students in making hard problems simpler. Combining this with earlier developing understandings that results from solving simple equations to make the two sides equal, in this case, 3x equals 27, means 3 times an unknown number equals 27, or 3 times 9 equals 27. Pause for Activity 2. The core of algebraic thinking is building, expressing, and generalizing mathematical relationships. So what is generalization? It is a statement that describes a general truth about a set of data. As in the statement, the sum of an even number and an odd number is always odd. We could have students memorize this rule, but then they would not have an experience with using the rule to help them with their computations. Instead, when choosing or creating computation problems, think about the generalization you want the students to focus on and choose problems that reflect that generalization. This way, a student gets practice with computation while at the same time learning to look for patterns and relationships. Look at the examples here. Each of these problems, no matter how big or small the quantity in the equation, holds to the rule that the sum of an even number and an odd number is always odd. Here are some additional number sentences that prepare students to think algebraically by looking for patterns or generalizations. Students would need many more examples than what we have provided here, but these are examples that will help you begin to think about how you might restructure what you are already teaching. These examples link back to the goals of building on student knowledge and helping them make connections. The first number sentences demonstrate the generalization that when you add 0 to a number, you get the number you started with. The next demonstrates that when you subtract a number from itself, you get 0. And the last one shows that when you multiply a number times 0, you get 0. All of these generalizations build on previous knowledge. Take the last one, for example. Students will build on their understanding of sets. They may interpret the problem 96 times 0 equals 0, as I have 96 sets with nothing in every set, so I have 0 in each set. Here we have another example of having students use what they know about composing and decomposing numbers to perform operations and create an opportunity to identify generalizations. This also demonstrates the use of multiple representations. The problem to solve is, Cammy the dog will herd all of the sheep into 2 pens. How many ways can Cammy herd the sheep into the pens? Have the students start by figuring out how to herd them all into a single pen. You can then show the student the equation 7 plus 0 equals 7. Next, the student moves one sheep to another pen that results in the equation 6 plus 1 equals 7. Next, the student moves one more so that one pen has 5 sheep and the other has 2. The resulting equation is 5 plus 2 equals 7. And the process can continue. Use a process like this. The students will find that there are 8 ways for Cammy to herd the sheep into 2 pens. You could repeat the same activity with 10 sheep, or 4 sheep, or even 25 sheep. In repeating with different numbers of sheep, the students can learn to detect that there is a pattern for how many different ways the sheep can be herded into 2 pens. Eventually, they can learn that the total number of sheep plus 1 represents the pattern. This generalization at the middle school and high school level might be represented using the symbol n plus 1 equals blank. Starting with a problem that is concrete or pictorial and moving to the symbolic representations helps students learn to generalize and use variables. The next question teachers should think about including in their instruction is whether or not the rule works in other similar problems. Pause for activity 3. Remember that it is important that students are not just learning answers to individual problems, but they are learning to use what they know to figure out the unknown and detect patterns and generalizations. If students are to be successful in algebra, instruction and experiences like those described in this presentation start in elementary school and must be a part of their ongoing mathematical instruction. This explicit focus on noticing patterns, communicating generalizations, and using symbols is important in supporting learning so that students are able to make connections, describe, justify general patterns and regularities in operations and properties of numbers. Remember these key principles in designing instruction that will build these skills and understandings. Provide multiple means of representation. Ask questions that encourage thinking. Build on student understanding. Help students make connections, describe, and justify general patterns and regularities in operations and properties of number. For more information about the Dynamic Learning Maps alternate assessment system, please go to www.dynamiclearningmaps.org. Thank you for your participation.